In the past, we classified bonds as either ionic or covalent. Ionic bonds transfer electrons, covalent bonds share electrons, in order to give everybody an octet. We can actually break down the covalents a little more specifically, and we'll classify them as nonpolar covalent or polar covalent. In this nonpolar covalent bond, electrons are shared, and they're shared equally between the two atoms in the bond. Here's how this happens. It's all about electronegativity. That's an H, kind of a funky looking H. There we go. And here it says electronegativity difference. I would instead, let's just look at electronegativity values. The electronegativity values of the two atoms in the bond are the same. So if we remember electronegativity, it's the ability to attract or steal electrons. If you have two atoms with about the same electronegativity value, they'll both have the same pull on the electrons. And essentially, the electrons are shared right smack in the middle of the two nuclei. So if these black dots represent the positive nuclei, we would have two electrons shared right in between those two atoms. They'd be shared equally because each atom has the same pull on the electrons. Think of it as like a tug of war between identical twins or something like that, where they're both pulling on the electrons with the same force in opposite directions. So really the electrons are like the flag on the rope, ends up being right in between the two nuclei. So here's where these penguins and polar bears come into play. If you had two polar bears sharing ice cream, assuming that they're both hungry for ice cream, they'd probably share the ice cream equally. Two penguins would share the ice cream equally. The best example of these nonpolar covalent bonds are between identical atoms, and specifically the diatomics. H2, N2, O2, all the halogens. If it's the same atom bonded to itself, of course it has the same electronegativity value. The electrons will be shared exactly the same. This word nonpolar means that the ends of the molecule are exactly the same. There is no one region that has more electrons than the other. The electrons are shared right smack in the middle of the two atoms. They're shared equally because electronegativity values are the same. Not the case with polar covalent bonds. Now again, it's covalent, so electrons are shared, but they are not shared equally. Not shared equally between the two atoms in the bond. So again, when they talk about electronegativity difference, let's just say electronegativity values are different. This time the electronegativity values of the two atoms in the bond will be different. And again, we're talking covalent, so it's still nonmetals. But let's say we had hydrogen bonded to fluorine. And I can just look on a periodic table and I understand the general trends in electronegativity. And I remember that fluorine had the highest electronegativity on the whole periodic table. It's a pretty small atom. It's got a strong nuclear charge. So there's a strong attraction for negative electrons. Now if you have fluorine bonded to little baby hydrogen with just one proton and one electron, the electronegativity of fluorine is so much higher that they might share, but they do not share equally. This arrow is supposed to show that the electrons in the bond are more attracted to the fluorine. So this time they would not be directly in between the two nuclei. if I had 2 electrons in here, they'd be closer to the fluorine. See if I can tuck in 2 tiny electrons. Closer to fluorine, because he has the higher electronegativity. Let's put that in there too. Electrons are closer to the atom with a higher electronegativity. With a higher electronegativity. Well, that makes sense, because again, electronegativity is the ability to attract or steal electrons. If fluorine is higher, they might share, but they're not sharing equally. The electrons will be held closer to the fluorine. Now, last time I checked, electrons are negative. That creates a partial negative charge. If the electrons are closer to the fluorine side of the molecule, we use this Greek symbol, it's kind of a little squiggly thing, partial negative, to show that the fluorine side of the molecule is slightly negative. It's not a full transfer of electrons, so we're not going to say -1. The electrons are just drawn closer to that end of the molecule, and so we'll say it's partially negative, which then leaves the hydrogen end of the molecule partially positive. It's got a lack of electrons, partially positive, not -1. We're not going to give away the electron. It's just held closer to the opposite end of the molecule. Which then, that is what polar means. When we say polar covalent, or a polar molecule, we mean the ends are different. One end is slightly positive, one end is slightly negative. Ionics are always polar. An ionic bond is always polar. One end is a full +1 or +2. The other end is a -1, -2, -3. The ends of the ionic bond are different. They're charged. We can say the same thing about these polar covalent bonds. The ends of the molecule or the ends of the bond are different. One side is slightly negative and the other side is slightly positive. So this picture is supposed to show that if a penguin was sharing ice cream with a polar bear, and the polar bear was kind of like the fluorine, and the penguin was kind of like the hydrogen, the polar bear, assuming that he's more aggressive, maybe hungrier, is probably going to get more ice cream. Kind of like in this bond, the fluorine gets a larger share of those 2 electrons. These are very, very common. They occur between nonmetals, because it is a covalent compound, and it's usually different nonmetals, because now the electronegativity values will be different. And then finally, there are ionic bonds where the electron is transferred. So we've got our positive and negative ion. One electron is transferred from the positive to the negative. We completely add that electron to the negative ion. And again, now it's not just partially positive or partially negative. This is where you get the full charge. +1, +2, -1, -2, -3. The electronegativity difference between the atoms in this ionic bond is extreme. The atoms will have very different electronegativity values. If you think about ionics, they have a metal bonded to a nonmetal. Ionics have very different electronegativity values between the 2 atoms. The nonmetal has the higher electronegativity value, because if you look at their spot on the periodic table, the nonmetals are where we already have like 5, 6, 7 valence electrons. They really want to gain more electrons. The metals are positive ions. Those have low electronegativity values. They don't want to gain electrons, they want to lose electrons. So they have very different electronegativity values. And again, sodium chloride is a great example, where the electron is totally transferred, And this charge is like a full out -1. It's not just partially negative. It's a full negative charge. We gained electrons, and the other side would be a full out positive charge, negative charge. And so again, it says in this little cartoon now, the polar bear is just going to take the ice cream. At the extreme of difference in electronegativity, polar covalence shades into the winner-take-all situation of ionic bonding. The more electronegative atom just totally seizes all the bonding electrons to become an ion. Completely transfers all the electrons. And now in reality, it's not like the penguin is real disappointed about this. I don't know, maybe he's like lactose intolerant or something. Because if you think about sodium, he willingly wants to lose that electron. He has one valence electron. He wants to lose the electron. Then what's left will have a full outer shell. So again, we can get a little more specific with the covalent bonding. It's all like a degree of sharing. The nonpolar bonds share equally. The polar covalent bonds share electrons, but they do not share equally. They're just drawn closer to the more electronegative element. And then in the ionic bond, we're not sharing at all. It's like the worst sharing. The electron is totally transferred.